Hi everybody, today I will talk about the synthesis and characterization of smart nanofertilizers based on nitrate-doped calcium phosphate nanoparticles. If we look back at our past, global population increased much more than the available arable land, so that the increasing food demand was addressed by increasing the crop yields with the massive use of fertilizers, providing main macronutrients as nitrogen, phosphorus and potassium to the plants. However, conventional fertilizers are highly soluble salts characterized by very low efficiency, as most of the nutrients are washed away by rainwater, causing severe environmental issues and the waste of non-renewable sources. And this is an unsustainable approach, considering that global population will increase in the future and fertilizers are necessary for food production. Moreover, the current exploitation of phosphate ores is expected to reach a peak in the near future, so that a more sustainable use of resources should be devised. In particular for phosphorus, its future demand is expected to be much higher than the availability, so to cope with this problem, several practices should change, focusing on the reuse and recycling of phosphorus and increasing the efficiency of the processes. And among them, increasing agricultural efficiency is a key point for the future development of sustainable agriculture and the main focus of this work. In fact, we were inspired by biogenic apatite, which is the inorganic fraction of bone, to design a new type of fertilizer, a smart fertilizer, much more efficient than the conventional ones. And this is obtained with this nanocrystalline phase, which is much less soluble than the conventional fertilizers, but inherently rich in phosphorus and prone to ionic substitution, in particular carbonate, which is the major one, but other ions can enter the structure. So we explored the possibility of introducing nitrate within the structure of apatite, making this a promising material to be engineered for agricultural applications. The synthesis is quite simple, following the green chemistry principles, and we prepare different samples, a reference, undoped sample, and nitrate-doped samples. Starting with the two solutions with the precursors, we mix them and we obtain a suspension, and the material in the suspension is at first an amorphous phase as amorphous calcium phosphate, transforming into apatite upon maturation time. And this is clearly seen with the wide-angle X-ray total scattering experiments, where you can see a completely amorphous trace at the bottom for the amorphous material, transforming progressively into apatite after 24 hours. No other phases were detected, so the nitrate detected by infrared spectroscopy and elemental analysis is actually incorporated into the material or adsorbed at the surface. Focusing on the nanocrystalline material, preliminary analysis showed that this sample is partially composed by an amorphous phase, accounting for nearly 30% of the sample. So we wanted to explore the relationship between amorphous and crystalline phase within the sample. To do this, we rely on small angle X-ray scattering technique, which is blind at the atomic scale but sensitive to define size and shape of nanoparticles at the nanoscale. At first, we measure the amorphous material, and the experimental trace was modeled with a single population of spherical nanoparticles. Conversely, the sample at 24 hours was modeled with a single population of nanoplates. This means that these nanoplates are a composite material formed by an amorphous and a crystalline phase, because no traces of spherical particles were detected in this sample. To integrate this information in the wide angle, we used a unified model for SAXS and WAXTS analysis based on the Debye scattering equation, which can compute the scattering pattern in the Q range measured by both the techniques, and starting from the same atomistic model. And this approach will benefit of the length scale complementarity of the two techniques. So at first we built an atomistic model of nanoparticles at increasing size and desired shape, and from this atomistic model we simulated the scattering pattern for the small angle and wide angle X-ray scattering, and we refined several parameters to fit the experimental data. So the analysis of the small angle X-ray scattering data provide the information on the size and shape of the entire nanoplate, whereas the analysis in the wide angle provides size and shape of the crystalline fraction together with the microstrain information and the quantification of the amorphous phase. Allocating the amorphous and the crystalline phases within the nanoplates can be done with two different models. One, a core shell model, where the amorphous material is distributed along the surface of the crystals, or a core crown model for which the amorphous phase is mainly allocated on the width and length of the plates. And the latter is the model that better fit our data. We wanted to explore the possibility of nitrate incorporation, so that we analyzed the unicell parameters for several samples, the undoped one, and samples at increasing nitrate content. And we see compression in the A-axis and expansion in C at increasing nitrate content. And this can be actually interpreted as a the effect of nitrate incorporation. However, nitrate entered in the crystal structure apatite in a way similar to that of carbonate. So disentangling the two contributions from nitrate and carbonate substitution within the apatite and quantifying it is not easy at this stage. But further hints of the effective nitrate incorporation can be obtained by analyzing the chemical stability and dissolution kinetics of these materials. We put these materials, the amorphous and the nanocrystalline, in water suspensions, and we measure the calcium release and nitrate release. Samples are definitely stable in water. They were put in undersaturated conditions. And we measure calcium release for the completely amorphous phase, amorphous material, and the nanocomposite and the nanoplates material. The release of calcium is also indicative of the phosphate release because of particle dissolution. As you can see in figure B, calcium release for the amorphous phase is much faster than the release for the nanoplates. Moreover, the behavior of dissolution kinetics of the nanoplates follow two different regimes. The first one, in the first hours, is much similar to that of the amorphous material, and this can be interpreted as the dissolution of the partial dissolution of the amorphous located in the width and length of the plates. Whereas the calcium release slow down at longer time, and this dissolution may be due to the exposure of the basal faces of the plates and to the dissolution of the crystalline core. Interestingly, if we are looking at nitrate release, we can see that nitrate incorporated in the amorphous material is much higher in quantity, but the release is much faster, as you can see in figure D. And this is interpreted as a weakly bound nitrate molecules at the surface of the particles, whereas a completely different behavior is obtained for the nanoplates. We can see a burst effect of nitrate release that is probably due to nitrate loosely bound at the surface, but after that a very slow and controlled release is matching the calcium release at a longer time with the same kinetics. And this can be interpreted as indicative of nitrate, a slow nitrate release that is paired with the dissolution of the particle. And this is a major hint of nitrate incorporation within the crystal lattice. So concluding, we can prove that slow and controlled release of macronutrients is possible by modulating the size, the structure, and the composition of nanoparticles. And these are promising results for future application of these materials as smart nanofertilizers. These results may also have implication on the biomineralization study useful for bone and teeth reconstruction. If you are interested in more details, two recent papers were published with details on the model and results presented in this talk. And I wish to thank all the people involved in the project, and I really want to thank the young Italian crystallographers for organizing this event. And thank you for the attention.